Hello and welcome to this talk. This talk is about the paper titled Diverse Collections in Matroids and Graphs. I'm Philip and this is joint work with Fedor Fomin, Petr Golovach, Fahad Panolan and Saket Saurabh. So let me start with an introduction to this diverse X paradigm. The motivation behind this paradigm is the observation that most algorithms are about finding one good solution to a problem. So given an input, the algorithm finds one output of a specified kind, and there is a notion of what is good about the output, some metrics such as the size of the output or the cost of the output or some such. And essentially every algorithmic paradigm is of this form. All are about finding one good solution. A notable exception to this are enumeration algorithms, where the goal is to find all solutions or all solutions of a specified type, such as all maximal solutions or all minimal solutions. So what's the problem with finding one solution? For problems which are motivated by the real world, it often happens that the solution that we find, the one good solution or the one best solution that we find, may not be of much actual use. And the underlying reason behind this is that the modeling process, which takes the real world problem and makes it into a nice algorithmic problem, that process throws out a lot of relevant side information, so that the eventual nice problem that we solve is just a skeleton of the actual real world problem. Let's see a brief example to demonstrate this. Recall the vertex cover problem, where we have an input graph on n vertices, and the goal is to find a vertex cover of this graph of the smallest size. An application of vertex cover is in conflict resolution. So each vertex in this graph, this conflict graph, will be a real world entity, and we will put an edge between two entities if they are in conflict as per some definition of conflict. And a specific example of this in action is decision support systems for air traffic controllers. In this case, the vertices in the conflict graph are aircraft, and there is an edge between two vertices if there is a chance that the corresponding aircraft may interfere with each other. And a small vertex cover of this conflict graph gives us a small set of aircraft to divert from their current paths, so that the chance of interference goes away. Now, if you think for a bit, it will become clear that all small vertex covers of a given conflict graph in this situation are not equally good. The vertex cover problem, the formulation, ignores all of this real world complexity and just focuses on which two aircrafts are in conflict. So one smallest vertex cover of this conflict graph may actually be totally useless for an ETC to solve their real world problem. On the other hand, finding all small vertex covers or all minimal vertex covers is also not a good idea. Firstly, it's very hard to do this because there are just so many such vertex covers, and even if we manage to somehow do this in a reasonable amount of time, the output is so huge that it just overwhelms the ATC and it's totally useless for them, for their purpose. So what is the diverse X paradigm? This is a solution to this kind of a problem. The idea was proposed by Mike Fellows, and in this the letter X stands for some algorithmic problem such as vertex cover. And the idea is to find, instead of one best solution, find a small number of solutions of good quality, such that any pair of these solutions are far away from one another by a relevant metric. So in the case of the aircraft example, instead of finding one set of, let's say, 10 aircraft to divert, in the diverse X paradigm we would find, say, 5 sets of 10 aircraft each, where diverting any one of these 10 aircraft sets will eliminate interference, and no two sets of aircraft share more than a few, let's say 5 aircraft. So this corresponds to finding a few small vertex covers of the conflict graph where no two of these vertex covers have many common vertices. Such a solution, such a collection of widely varying solutions would be much more useful to the air traffic controller to solve their problem. Now the challenge is, can we do this? Can we do this fast? How can we do this fast? The idea of looking for diverse solutions is a fairly recent development in the world of parameterized algorithms, and there are only a handful of results known. The very first work in this area was by Baste et al. In HKI 2020, where they showed that the diverse variants of many graph problems are fixed parameter tractable, where the parameter is the tree width of the input graph plus the number of solutions required in the collection of diverse solutions. In another work, Baste and another group of authors, they took up the diverse variants of the D-heating set problem for a fixed D. They showed that a certain variants of this problem are FPT, where the parameter is the size of the heating set plus the number of solutions. In more recent work, Hanaka et al. Have shown that a large collection of diverse problems are FPT. For instance, finding diverse sets of spanning trees, paths, matchings, subgraphs, and matroid bases. In our work, we look at 3 specific problems. 2 of these are about matroids and 1 is about graphs. In each of these problems, finding one optimal solution is known to be easily solvable. It's known to be solvable in polynomial time. And for all these 3 problems, we show that finding a small collection of diverse solutions, first, it's unlikely to be solvable in polynomial time. Second, it's fixed parameter tractable with the parameter being the number of solutions plus the minimum Hamming distance or the minimum weighted Hamming distance between every pair of solutions. The diversity measure here is the minimum Hamming distance between pairs of solutions or the minimum weighted Hamming distance. We assume in our problems that the input matroids are given as independence oracle. That is, we are not really given the entire set of independent sets. Instead, there is a black box algorithm which, given any subset of the ground set as input, subset X, it will tell us in constant time whether this subset is independent in this matroid or not. The first problem that we look at is called weighted diverse bases. So here the input is again a matroid in the form of the oracle, and there is a weight function which takes elements of the ground set and gives them positive integral weights. There are 2 numbers k and d, 2 integers k and d, and the question is, does this matroid have k many bases b1 to bk such that the weight of their symmetric difference is at least d for any pair of these bases. So here the symmetric difference is defined, this triangle denotes the symmetric difference of these sets, and the weight of a subset is just the sum of the weights of its constituent elements. This is a generalization of the classical matroid based packing problem, which is about finding a maximum number of pairwise disjoint bases of a matroid, and this has long been known to be solvable in polynomial time. There are many interesting special cases of weighted diverse bases. For instance, we can represent these problems as instances of weighted diverse bases: finding diverse spanning trees in an edge weighted graph, finding diverse column bases of a matrix with column weights, and finding diverse systems of distinct representatives on a weighted ground set. We first show that this problem is strongly NP complete even on the uniform matroids U3n. We also show that even when all the weights are just 1, so we are just counting and not weighing, and the diversity measure is just 1 again, even in this case this problem has no polynomial time algorithm unless p equal to np. On the positive side, we show that a weighted diverse basis is fixed parameter tractable in the parameters d and k, and we also show that if we are given the input matroid as a representation over the finite field GFQ, then we can in polynomial time compute an equivalent instance of polynomial size. The size is polynomial in k and d and logarithmic in q, so we can compute a kernel for this problem, provided the input is given as a representation rather than as just an oracle. The second problem that we look at is called weighted diverse common independent sets. Here we have as input two matroids on the same ground set E, two matroids M1 and M2, and as before, a weight function which gives positive integral weights to elements of the ground set, and two numbers, two integers k and d. The question here is, can we find k sets, k subsets of the ground set where each of these sets is independent in both of these matroids, and the weighted Hamming distance of any pair of these is at least d. This is a variation on the classical matroid intersection problem, or the weighted matroid intersection problem, which is about finding one maximum sized common independent set of two matroids, or one maximum weight common independent set of two matroids. And these problems have been known to be solvable in polynomial time for a long time. This problem also has many interesting special cases. For instance, finding a diverse collection of matchings in an edge-weighted bipartite graph, finding partial orientations of an edge-weighted graph where these orientations are diverse, or finding a diverse collection of colorful forests in an edge-weighted edge-colored graph. We show that this problem is also strongly NP-complete on the uniform matroids U3n. On the positive side, we show that this problem can be solved in FPT time in the parameters d and k. The third problem that we take up is a graph problem. It's called diverse perfect matchings. The input is an undirected graph G and two numbers k and d, and the question is there a collection of k perfect matchings m1 etc mk in the graph such that the number of edges in the symmetric difference of any pair of these is at least d. This problem generalizes firstly the problem of finding one perfect matching of a graph, which is solvable in polynomial time, and also the problem of finding two disjoint perfect matchings, which somewhat surprisingly happens to be NP-complete even in three regular graphs. We show that the diverse perfect matchings problem has no polynomial time algorithm unless p equal to np, even when the input graph is bipartite, and even when we are just looking for k matchings which are just different, where the diversity measure is just 1. On the positive side, we show that this problem can also be solved in FPT time, but here the algorithm is randomized and has a constant probability of success. In the rest of this talk, we will go over a brief overview of our results. First, we take up weighted diverse bases, where we are supposed to find a collection of bases whose weighted Hamming distance is at least d. We first show that it is NP-complete even on the uniform matroids U3n. This is by reduction from the three-partition problem. The input to the three-partition problem consists of a positive integer b and a multiset of 3n positive integers x1 to x3n, where each integer xi in this multiset is strictly between b by 4 and b by 2, and the sum of all the xi's is exactly n times b. The question is, can we partition this set S into n multisets S1 up to Sn, where each Si sums up to exactly b. So it's easy to see that if the three partition problem is a yes instance, then each multiset in the solution must have exactly 3 elements. Using this, we show that if we look at the uniform matroid U3n on the underlying multiset 1 to 3n, and keep the weight of each of these elements, each of these numbers, the weight of number I as xi, and set the diversity measure to be 2 times b, then this is indeed a reduction from three partition to weighted diverse basis on the uniform matroid U3n. we show that weighted diverse basis has an FPT algorithm when the parameter is D and K. Let's see a brief overview of this algorithm. So for this we need the notion of a dual of a matroid. The dual M star of M is another matroid on the same ground set, such that the bases of this dual matroid M star are exactly the complements of the bases of M. We say that a subset S of the ground set is co-independent in M if S is independent in M star. Now it is known that we can find in polynomial time a subset of the ground set of M of the largest size, such that this subset is both independent and co-independent in M. So this we can do using matroid intersection. So what we do is we find a largest subset of the ground set which is both independent and co-independent in M. Now if this subset is at least has size at least kd by 2, then it is not difficult to see that we can construct k bases which satisfy the diversity constraint. So we report yes, which means that we can assume without loss of generality that the size of a largest set which is both independent and co-independent in M is strictly less than kd by 2. Now our algorithm does the following. It starts to start with it uses the greedy algorithm to find a heaviest basis B0 of M. It then deletes the elements of B0 from the ground set of M to get a matroid M1, and now it goes and finds a basis B1 of M1. Then it deletes the elements of B1 from the remaining ground set to get another matroid M2, and so on. So it repeats this process some poly kd many times, and then we show that from the set of elements which got deleted in this process, we can construct a set S star which is a subset of the original ground set, such that the size of S star is poly in K and D, and we can also construct a matroid M hat on S star such that solving a weighted diverse basis on M hat WKD is equivalent to solving it on the original instance M WKD. So now we have what we have done is we have found an equivalent instance of size which is bounded in a polynomial in K and D. So now we do an FPT time search for diverse bases in this smaller matroid, and that completes the algorithm. The kernel for this problem also follows along the same lines. So in this case we are given a representation of the matroid M over GFQ. What we do is we'll construct the matroid M hat just like in the algorithm, and we show that each of these steps can be mimicked over the representation, so that we end up with a representation of M hat, and it's not difficult to see that this representation has in fact the required size bound. So this is the kernel. So now we move on to weighted diverse common independent sets. This is again NP complete even on the uniform matroids U3n, and the reduction is again from 3 partition, and this reduction is in fact nearly identical to the reduction for weighted diverse basis. We show that weighted diverse common independent sets can be solved in FPT time in D and K. Here is how we do it. We first find a largest common independent set of M1 and M2. This is similar to what we did in the previous algorithm. We do this using the algorithm for matroid intersection. Now if this largest common independent set is of size at least kd by 2, then it is not difficult to see that we can construct these independent sets I1 to Ik which satisfy the diversity condition. So in this case we report yes, which means we can assume without loss of generality that the size of a largest common independent set of M1 and M2 is strictly smaller than kd by 2. Now given this, our algorithm does the following. What we do is we do branching. We use a recursive FPT time branching to construct a collection F of common independent sets of M1 and M2. This collection has size FPT in K and D, and more importantly we show that if the input is a yes instance, then there is a set of independent sets I1 up to ik such that each of these independent sets I1 to ik belongs to this collection F. And given this and given that the size of this collection is fpt in dnk, to complete the algorithm, we do an fpt times search in the collection F to find the solution. Finally, we look at diverse perfect matchings. So here the input is no longer a matroid but it's a graph, and we are looking for perfect matchings which are diverse. This is known to be NP complete even when we are looking for just 2 perfect matchings and the input graph is 3 regular. We show that it's in fact harder in some sense. We show that even if the graph G is bipartite and we are looking for a diversity of 1, we are just looking for different matchings, it's still hard. So to see this, observe that all perfect matchings of the graph have the same size, and a graph, bipartite graph for G on n vertices has at most n by 2 factorial perfect matchings, which the logarithm of this number is order n log n. Now if we set the diversity measure D to be 1, then the diverse perfect matchings problem translates to the question, does G have k different perfect matchings? And again, now by doing a binary search on k, we can count the number of perfect matchings of the graph in order n log n invocations of an algorithm for diverse perfect matchings. But we know that counting the number of bipartite perfect matchings is sharply complete, and therefore a diverse perfect matchings problem has no polynomial time algorithm unless p equal to np. On the positive side, we show that diverse perfect matchings can be solved in fpt time, fpt in dnk, using a randomized algorithm with a constant probability of success. What this means is that if the input instance is a no instance, then this algorithm will always correctly report no. If the input instance is a yes instance, then this algorithm will report yes with probability at least half. This algorithm works as follows. First, it greedily computes a maximal widely scattered collection F of perfect matchings. So what we mean by this is that the procedure is greedy. It keeps finding, to build up this collection, it keeps finding matchings one after the other, and the Hamming distance between any pair of matchings is that it finds is large. If we end up with a collection F of perfect matchings which contains at least k many matchings, then because we insisted that every pair is at least d away, we can immediately return yes, we have actually found a collection of perfect matchings which satisfy the condition in the question. If you look at any solution m1 to mk for the problem, then for each matching in this solution, there is a unique matching in our collection that we built up which is close to mi, which is not far from mi. And now what we do is, given that so given this collection of perfect matchings, what we do is for each perfect matching m hat in F, we guess the number of r hat of matchings in m1 to mk which are close to m hat. Then we compute this r hat many matchings which are close to m hat. We show that this can be done in fpt time, and we also show that taking the union of all the matchings that we computed in this manner for different elements of m hat, if you take the union of all those matchings, that is a solution. To summarize, we looked at 3 problems, 2 from matroids and 1 from graphs. We showed that weighted diverse spaces, weighted diverse common independent set are NP complete, and diverse perfect matchings has no polynomial time algorithm even on bipartite graphs unless p equal to np. And then we showed that each of these problems is fixed parameter tractable, where the parameter is the number of solutions plus the minimum diversity of a pair. And we also showed that weighted diverse basis has a polynomial kernel provided the matroid is given in the input as a representation. Now, as I said, this is a very new area in parameterized algorithms, so there are lots of problems which are open. Let me focus on problems from Matroids. The immediate question is about finding diverse variants of other interesting and well-studied structures in Matroids, such as circuits, flats, hyperplanes, and so on. Thank you for your attention.